Okay, so appreciate the introduction. As you mentioned, we're going to be talking about PHI's low energy building standard, particularly for multifamily buildings. So, just a quick note about so our company and my background. I've been at Stephen Winter Associates for over 8 years now. I've worked on our Passive House team exclusively, have a lot of experience across a lot of different project types. Multifamily is the main type that I've worked on, and have a large amount of experience just sort of looking at passive house energy models, doing on-site verification, reviewing construction submittals, all of the, beginning to the ends of projects, and want to bring that experience. But our company, we don't just do passive house, we do all elements of sustainability consultant, accessibility, decarbonization, all across the Northeast corridor, from DC up to Boston. We have offices. So that's just a little bit about me and us. I want to just start off by the why. So, like, why are we talking about this? Why is this coming up? Well, I think at a starting point, I do think this is a really, really important time for the construction industry. Um, I'm sure this is true globally. I work primarily in the US market, and the majority of the projects that I work on are in the Northeast. And in that specific market, this is a really important time for the construction industry. There's threats of tariffs, and construction costs are high and not going down. Construction is slowing across the board. If you look at AIA's architectural billings reports, those have been going down over the last couple of years. So, but at the same time, we need affordable housing. We need housing in general across the board, especially in these areas, and urban environments, suburban environments, really across the board. Um, so it had me thinking a lot about, how are we addressing the construction industry? How are we thinking about scaling up low carbon design, passive house design? It's also an important time for the planet. I don't think I need to really dwell on this too much, but just pulled up the latest from IPCC, the Intergovernmental Panel on Climate Change. Just for folks that maybe aren't aware, um, emissions are still going up. We're right now at a time where it's a pivotal point for really decarbonizing, and we do still have the ability to make a big impact. Right now, the implemented policies as such, per the IPCC, will result in really still a significant amount of carbon emissions, and to really limit global warming potential to 2 or 1.5 degrees C, which is really an ideal goal. We have to do something, and this is what in this report they say, you know, to get to these levels of global warming potential, or limit the global warming in terms of 2 degrees C or 1.5 degrees C, we have to still make a big jump in reductions of emissions levels, even when looking at this compared to 2019 emissions levels. So these numbers here are percentages and ranges of reductions from 2019 levels just 6 years ago that we still need to make. So this is why I joined this field of building design and passive house design, is sustainability, addressing the climate crisis that we're in. We can make an impact. We, as passive house designers, or for folks on this call that are maybe on the design side or developer side or policy side, wherever your role may be, we are the ones that can make an impact. And I live with this question and concern in my brain all day. How can I and how can we make an impact to help address this problem? And I think PHI LEB plays a really, really, really big role in this, or can play a really big role in this, especially now. And before diving into this standard, I want to just talk about just sort of the origin story of this standard for me. So we're going to go back in a time machine 6 years ago to 2019, and a town in Massachusetts, Newton, Massachusetts, just west of Boston, not too far from it, greater Boston area, and a project that many of you probably have heard of on other presentations or conferences, the Northland Newton development. And This is, as you can see, a very large scale mixed use multifamily as the main kind of use type there, development in Newton, Massachusetts. This is from 2019. There are some sort of shifting in the plans that are kind of under works right now, but the general concept of this development is still intact. Um, so back in 2019, we engaged with the design team and ownership on this project. It's 13 buildings. Most of them are multifamily mixed use. There's over 800 apartments. About 18% of those are affordable. And for a few reasons, they made the commitment to go to passive house for buildings 3, 4, and 8. So three out of the 13 buildings that were on the site. And this accounted for about 275 units, 410,000 gross square feet. These buildings were anywhere from 4 to I think 5 to 6 stories or so. So large scale multifamily, I would say definitely falls into that category. Not super, super tall like you might see in a city environment, but still large scale multifamily. Um, in the state of Massachusetts for the last 4 or 5 years, there's been a really awesome incentive program by Mass Save that has incentivized passive house construction immensely and has been a huge part of the extreme growth we're seeing in the Massachusetts market. But they incentivize particularly feasibility studies, which I feel are one of the best ways to make a huge impact on a project is to just do a feasibility study, get your foot in the door, let the design team know what it would take to get to the passive house level. So we had that incentive available, and the client was very interested in looking at, well, we committed to these 3 buildings. It was their first commitment to passive house, so they didn't want to bite off more than they can chew. And they were interested, though, in what it would take to get to the passive house level for these other 6 buildings that they've identified here in pink. And in particular, we looked at this building, building 12, as it relates to the LEB standard. And I'll get into that in a minute. So this building was 4 stories, 31 units, 37,000 square feet. So it wasn't massive, but it was still big scale multifamily. It wasn't a townhome. It had over 30 units, starting to really inch into the realm of these bigger scale multifamily projects where we see that you get economy of scale, you get efficiencies in the surface to volume ratio of the building envelope. We see with these bigger projects as well that we don't need maybe as much R value in our wall or as high of a solar heat gain coefficient in our windows because we're getting the bigger the project, the more that the internal loads in the building dominate and the less that the solar loads have a role in there. Um, that said, solar loads do still play a very important role in passive house design, really, no matter how big the project is. And on this project, there is some major shading from the southern facing facades from the adjacent building. And this led to some big challenges. So, um, as a result of this shading, or taking a step back, just looking at sort of the baseline level of design specs that we were looking at for this project as a starting point, above grade walls of R33, roof R values of R57, windows, triple pane, highly efficient insulated glazing units with a U value of 0.16, SHGC of 0.37, center of glass. It's a solar heat gain coefficient, and ventilation heat recovery efficiency of 82%. So these are all, very good specs for a multifamily building. I think it's pretty common to see these levels of performance being required for passive house design in climates like Massachusetts and the Northeast in general. Um, so even with these specs, though, we struggled mightily to meet the class of passive house classic criteria. And I'll get into the different categories in a minute, but the conventional passive house criteria that I think most of the industry is familiar with um, has limits on heating demand and limits on cooling demand and primary energy, which is source energy for the building. And we were nearly double the heating demand of the PHI classic criteria as a result, largely due to this shading. So we were like, what do we do? We want this project to still commit to a high level of performance. Something like passive house, we just have no way of getting there. There's no solar heat gain coefficient that's high enough that we can get this heating demand down. There's no R value big enough or large enough that's gonna wall size that's large enough to help get this heating demand down. So we were just kind of like felt like we had our hands tied behind our back. So we called Passive House Institute and said, what can we do? And that's when they actually introduced the LEB criteria to us. They said, well, we have this alternative criteria called PHI LEB, and it's reserved for, or it can be used for projects that just can't meet the classic criteria, and for whatever reason that may be, if it's shading or whatever it might be. So it was really insightful to get this piece of information and recommendation from them, and um, it led to some interesting further discussions, so which I'll get into in a minute. But before diving into that, I want to talk about now just sort of what the LEB standard actually is and what are the mechanics of this? So within the criteria, this is the latest version 10C from PHI. They talk about the different levels of certification for a project. And the ones that we're probably most familiar with is the Passive House Classic. There's sort of upgraded levels to that, plus and premium, particularly for projects that have even lower energy use intensity and even greater renewable energy production. But PHI Classic is sort of the most, I'd say, widely adopted standard for buildings. There's also the Enerfit standard, which is for retrofits, which I won't talk about here. And then they talk about the PHI Low Energy Building standard in that criteria as well. So this is just straight from the criteria. It's, buildings which do not comply with one or more of the Passive House or Enerfit criteria may still satisfy the PHI Low Energy Building standard. So, as far as the actual thresholds are concerned, how are they different than the classic thresholds, the PHI classic thresholds? I want to show this as a representation of where this project, Northland Newton Building 12, was at in terms of its modeled energy results from the PHPP model. So what you're seeing here are the the heating demand, cooling demand, air tightness, and primary energy renewables demand represented in a percentage. And the percentage is based on the PHI Classic criteria. So 100% is the PHI Classic threshold. So as I mentioned before, our heating demand for this project was nearly double, and that's why you're seeing that heating demand bar be almost 200%. For air tightness, this project was targeting 0.6 air changes per hour at 50 pascals, which is the PHI classic criteria. And the PER demand as well was a little bit over the threshold for PHI classic. So this is where we were. The PHI LEB standards essentially are this, and this is the heating demand and cooling demand thresholds are double. The air tightness thresholds are 60% greater. So going from a 0.6 air changes per hour at 50 pascals to 1.0 air changes per hour at 50 pascals. And the primary energy renewables demand is about a 20% increase. So it's definitely more relaxed. And I think this is where there can be some hesitation or misconception about the standard that, it's just worse. And this is where I think um, we need to be careful because I'll get into in a minute in terms of basically what the opportunities for optimization are in these buildings. In other words, can we get a better balance between our heating demand and our cooling demands, and particularly our heating loads and our cooling loads, um, in these passive house buildings? And is PHI LEB a tool in our toolbox of standards for buildings to help achieve a more optimal balance between heating and cooling? I'll talk about air tightness in a minute, in terms of what the implication of going to that higher level is. And then as far as primary energy renewables demand are concerned, you get a little bit of allowance, but I think it's still very well within the margin of um, still steep energy reductions based on conventional construction. So the goals of the Passive House standard, we're probably all familiar with this, summarized here briefly: steep energy reductions, particularly in heating loads, or steep reductions in heating loads. Really steep energy reductions across the board for these projects, but where Passive House is really, really effective is at reducing heating loads. We're smashing down heating loads. It's also really good at providing occupant comfort, building durability and longevity, reducing potential for mold growth in wall systems and the like. Energy efficiency across the board is obvious, but it's also really, really good at ensuring quality control and construction verification for projects. So you have to do very detailed inspections and photographic um, documentation of the building as it's built. There's on-site verification of the ventilation system's performance and flows for ventilation air. And then there's, of course, the whole building blower door test where we're verifying airtightness for the project at the end of construction. These goals are achieved in both of these standards, PHI LEB and PHI Classic. Um, when we think about the design principles of the Passive House standard, continuous insulation, thermal bridge mitigation, air tightness, highly efficient windows, balanced ventilation with heat recovery, HVAC, and domestic hot water systems. Again, all of these design principles apply to the Passive House standard, both PHI LEB and PHI Classic. There's just differences in the thresholds that are considered passing or not passing, but the concepts and the principles and the goals are the same. So, just some other key differences with the PHI LEB standard versus particularly the classic standard. So air tightness. As I mentioned before, the PHI classic standard is 0.6 ACH 50. The PHI LEB standard is 1.0 ACH 50. There is, however, a specific clarification within the criteria that if a project falls between 1.0 ACH 50 and 0.6 ACH 50, that additional on-site leak detection must be carried out during the blower door test. So this requires typically the testing agency to really go around the building, look for air leaks, document what the air leakage is at that specific location where they may have found an air leak, document that air leakage before any sort of measures were taken to seal it, photograph it, seal it with any sort of measure that is on site, typically caulk or a spray foam product or a taping material, and then document how that air leakage was reduced um, after the seal was done on site. So you actually get this extra layer of quality control and verification of potential leakage areas that can still be addressed if it falls between 0.6 and 1 air change per hour. So yes, it's a more relaxed standard, but there's other strings attached to it that help ensure that it is, you're not resulting in any problematic leakage areas that could cause building durability problems. The other difference is the thermal comfort criteria is essentially waived for the PHI Low Energy Building standard. Um, Now, this I'm sure will probably get some questions, but my take on this, and I'll talk about the performance levels required to meet PHI LEB, but my take on this is that for one, for opaque surfaces, essentially, so these are non-windows essentially, so typical above grade walls, ceilings, floors. Um, in our climates, Northeast as the reference here, particularly, let's stick with Massachusetts, since we're talking about the Northland Newton development prior. You need about R8 in your opaque surface to achieve adequate thermal comfort. And this is actually a check that's done within the PHPP on the areas tab. And it's also a similar essentially check that's done on the Windows tab. So R8 is that threshold. You're not gonna really pass if your walls are not above R8. Where this really, I think, can actually have a big impact, though, is on the performance of windows that are required. So the thermal comfort criteria for that's required under the PHI Classic standard is a U value threshold for the overall window, and this is the installed U value of the window. So it counts for not only the glass, but the frame, the glazing edge spacer, and the thermal bridge that's created at the window to wall connection. That U value for Massachusetts is somewhere of an installed U value, somewhere around 0.16, 0.17, somewhere in that range. It does vary depending on the size and the mullion conditions. So there's a lot of nuances to what that criteria actually is. Um, but from our experience, it's a stringent criteria. This is not easy to meet. And not that I'm saying I expect necessarily all of these criteria to be easy to meet. It's the most rigorous energy standard in the world. But what we're finding is that it's oftentimes we're right on the edge of passing, or oftentimes just outside of passing that criteria. And we run into issues, particularly with this thermal comfort criteria. So more on this in a minute when we talk about specific design specs for projects. So jumping back to 2019 and talking about Northland Newton Building 12, we reran this project in the LEB criteria. Basically, in the PHPP, you can go in and change the pH classic threshold. You can just leave an option on the verification tab to select PHI LEB. And we saw that we were now meeting our heating demand and cooling demand, or heating demand threshold that was giving us the problems before. So it's an interesting, it led to an interesting follow-up to that. So as a result of those feasibility studies that we did, not only for building 12, but for these other 6 out of the 9 buildings that I talked about, again, those pink buildings, what the client realized was, hey, we can actually commit to the PHI LEB standard on these 6 other buildings. Like, we were introduced to this concept for building 12. I think there's no reason we wouldn't do it for building 12. So why wouldn't we do it for these other buildings, when we can expand our commitment to passive house, and the challenges of meeting classic on building 12 and some of these other buildings, which were heavily shaded, particularly on the southern facing facades. It just allowed a pathway for this client to expand their commitment to passive house. And what this meant was going from 3 buildings, which were the blue, to 9 buildings, going from 410,000 square feet to over 1 million square feet, and 275 units to 800 dwelling units, 800 plus dwelling units. So huge, huge improvements in terms of the scale of passive house commitment. And that was really made possible because of the PHI LEB standard. So as far as sort of the benefits that were provided, I'm sort of hitting on this already, but it allowed for scaling of passive house low carbon design. As I mentioned, basically across the board, we saw essentially a 3-fold, 2.5 to 3-fold increase, no matter which way you look at it, in terms of the scale of passive house commitment for this project. And this is something that I think is really, really important. It allowed for better alignment of the technical specifications across all 9 of these passive house buildings. So what I mean by that is we could have a similar wall construction and R value target for all of these buildings, which translates to similar details, similar wall types, if not the same wall types, which is really important for thinking about a development like this, where you have a lot of buildings and probably the same contractor for all of those buildings, and you want to benefit from these efficiencies of scale and efficiencies of similarity across buildings. I understand that not every building is the same, and the whole idea with passive house is that you're doing a model for each building and you're fine-tuning your design for each building. I'm a firm believer in that approach. However, I do think that when we can capitalize on efficiencies of scale in multiple buildings within a development, we should think about how we can take advantage of that opportunity. And PHI LEB allowed us to do that on this project. It'll also allowed us to have the same window specs for every building on site. So I'd mentioned for building Northland Newton Building 12, the U value of 0.16 and SHGC value of 0.37. We were able to get that window spec to work for all buildings. So the client could purchase one window for all buildings, which was key, because when you're talking about one window used for 1 million square foot of a development, there's a specific cost benefit to the economy of scale there, as opposed to having, let's say, 4 different windows or 5 different windows across the development, where you have to get specialized in terms of the specifics with those windows. So I think that was a huge benefit on this project. And it also allowed us to really just align and have the same HVAC and DHW systems and design approaches as well. So again, just alignment of technical specifications across a multi-building development. So just thinking about some inspiration here, because this isn't just inspiration for me. This is actually inspiration that was explicit from the client of this specific development. And there's a project in or development in Germany. I believe it's about 90 or so kilometers or 55 miles south of Frankfurt, in Germany, called Heidelberg Village. Many of you probably have heard of this already. It's a massive development. It's 116 hectares, over 2,000 homes, 162 apartment block. You're seeing just sort of a Google 3D view of all of those buildings. We want to make this happen here. It's Passive House has really grown in the last 10 years, and I feel like we're at a point where we can really help get to this level of large scale Passive House development. And I really feel that PHI LEB can help us get to this level, especially in our climate in the Northeast, which I will die on this hill and say is one of the hardest climates to design in, because it's really hot and humid in the summer and it's really cold in the winter. And each climate has their own challenge, but the Northeast is very challenging to hit this, to hit the stringency of the heating and cooling climate that we have, the extremes in this in the Northeast. So CNN did a great article on it, and they talked about a specific quote from the architect Wolfgang Frey, where they talk about this 5-finger principle, which is saying that to be truly sustainable, buildings must be ecological, affordable, innovative, integrative, and profitable. I do think that we need to think about the big picture when we're talking about our buildings, and not get too hyper focused on what do we need to do to hit 4.75 on our heating demand. I think that's critical. I think our approach to reducing the heating demand and reducing energy use in these buildings is critical, but we need to think about what's the impact that we're having at scaling up Passive House development, and what's the impact that these projects are providing in terms of not just sustainability, but affordability. So fast forward to another case study here. This one is in Middleborough, Massachusetts. So somewhat between or near Providence, Rhode Island, and Boston on the southern end of the state. And this was a more recent feasibility study that we had done. So this is a project that 76,000 square feet or so, 4 stories, 56 dwelling units. Nothing out of the ordinary in terms of a multifamily building. You can see a snapshot of the floor plan there. And as far as the exterior elevations are concerned, the window to wall ratio and facade types are very typical from what we'll see. There's nothing, I'd say, out of the ordinary about this building. To get to PHI Classic, we needed about an R33. And then to get to PHI LEB, we needed an R28. We still needed a pretty dang high level of R value to get there. It wasn't a huge gap in performance requirements for that envelope system between the two. When looking at windows for PHI Classic, we needed to go down to a U value of an uninstalled window U value of 0.14. For PHI LEB, we could walk that back to about a 0.16. Again, not a huge difference in overall performance. It's still a highly efficient triple pane insulated glass window to get to PHI LEB. It's not like we needed to go to we could walk that back to like a good double pane window. There's just no no opportunity for that. You still need to go to a very highly efficient window to meet this criteria. The solar heat gain coefficient is one that I think is where this issue has really started to grow in my mind in terms of how can we optimize our buildings for efficient design. And what I mean by that is for PHI Classic, we needed to go to an SHGC value of 0.45 to 0.47. Whereas with PHI LEB, we could reduce the SHGC value to a range somewhere between 0.33 and 0.40. So again, we have to meet our heating demand threshold. But one thing that I feel very strongly about as a not only a passive house designer, but a building consultant is um, being thoughtful about the design recommendations we're making. And when I'm sitting here going, what's more optimal, PHI LEB or PHI Classic, and thinking about the differences between the two, where I get worried is when we have to recommend window solar heat gain coefficients that are high, I'll say above zero point 0.4. These are center of glass values. Um, and then having to sort of ask the mechanical engineers, is this going to increase cooling loads to a point where we have to upsize our cooling systems? And that makes me a little queasy thinking about that question because my goal as a passive house designer is to help optimize this building, help reduce loads, not potentially increase them. And oftentimes when we're running energy models to try to get these buildings to pass the PHI Classic criteria and working through all the design specs of the building, it's so often that we come back to, well, we need to have a high SHGC value. We need to increase that. And it gets to a point where we're having to go above zero point 0.4 often. And that just is an uncomfortable feeling because um, generally speaking, with particularly the large scale multifamily, bigger buildings, especially the ones that are dense, that have a lot of internal loads, cooling is going to dominate these buildings, not heating. The cooling seasons are longer than the heating seasons. We're seeing heating seasons start somewhere in November and end in February, essentially, for passive house buildings, multifamily buildings in the Northeast. Um, the topic of window SHG was just sort of bringing to light of can we do better? Can we optimize these buildings? So that's it on the windows. I'm actually going to come back to this in a minute, but as far as the ventilation system is concerned, the big sort of impactful model input here is the sensible recovery efficiency of the ERV system. And on this specific building for Classic, we needed to go at a minimum of 85%, while for PHI LEB, we had to go down to 80%. So again, swing of 5%, not a huge difference, still a very high performance unit. And what I think we're also seeing is there's, I think, more options that are available on the market, even at a difference between an 85% efficient unit and an 80% unit. Um, if we can slightly relax that threshold or relax our ERV efficiency requirement from 85 to 80%, there's a chance that we open the door for more products to be available for these this project or for any project where we're looking at this. So just something to keep in mind. This development actually was also a multi-building development, so it's actually, I think, closer to 6 or 7 buildings, if I recall. And the building F that I mentioned before, which was again 76,000 square feet, 56 dwelling units. On the bigger side, when looking at another building in this development, which is a smaller one, 32,000 square feet, 3 stories, 24 dwelling units, a little bit closer to what the Northland Newton Building 12 was at. What we found was quite interesting. So um, what you're looking at here are in circles with the lighter shades is the building F requirements, and then the triangles with the brighter shades of pink and blue are the building A requirements. And what we found is that we needed essentially the same wall R values that we needed at building F for the classic and LEB standard. When looking at windows, we needed the same U value of the windows, or we essentially assumed the same level of performance for the U value of the window. But for PHI Classic, for the window SHGC value for this building, we needed it to go as high as 0.55 to 0.57, which again makes us a little uncomfortable when we're having to ask the MEP engineers, is this going to result in potentially an upsizing of our cooling systems? For PHI LEB, we can walk that back down to anywhere from 0.40 to 0.44 or so. And this was important because it allowed us to potentially get, again, the same window for both buildings. So we're seeing that benefit that I talked about on Northland Newton, where we were able to have the same window be suitable for multiple buildings in this development, which will help adoption of the Passive House standard and the scaling of across buildings and developments like this. And again, ERV sensible recovery efficiency, we needed to go to 85% for classic and 80% for PHI LEB. So still, again, a very highly efficient unit. So the last thing I want to just quickly talk about here is just the topic of cooling and keeping tabs on cooling here. Again, as I mentioned before, we, as Passive House designers in the Passive House design community, I think have an obligation to thinking about how we can deliver the most optimal energy efficient building. And one interesting study that I was involved in last year was a study that was funded through the U.S. Department of Energy. And we did extensive monitoring on 3 buildings, 2 of which were certified Passive House buildings and 1 which was a more conventional building. All 3 were large-scale, high-rise multifamily developments in New York City. So this is a climate that's a little bit less heating intensive compared to, let's say, Massachusetts or northward, but still very much that typical Northeast climate where it gets really cold in the winter and very hot and humid in the summer. The first building that I'll talk about is one that Ken actually mentioned earlier, Sendero Verde in Harlem, New York. It's particularly the Sendero Verde B South building. This is certified to the PHI Classic criteria. And as part of this study, we did our own load calculations and cross-referenced the mechanical engineers' load calculations and compared our results to theirs. There's a whole study that's going to come out with this, hopefully sometimes this year. Obviously, the state of the federal government is a bit in flux right now, but essentially what we found is that the cooling loads for the typical studio 1-bed and 2-bedroom apartments were at least about double, if not 3 times, what the heating loads were on this project. I'm going to jump to another project as well, where this is 425 Grand Concourse in the Bronx. This is the other one that we studied. This is actually a FIA certified project, so I know we're talking about the PHI standard here, but this is the project we studied. This is the data we have. I'm not going to get into the differences on this presentation. We can certainly talk about it in the Q&A between FIAS and PHI, LEB or Classic, but long story short, it's a Passive House building, right? It's those same design principles, those same goals. Cooling loads also about double what the heating loads were. So I'm looking at this and going, are there opportunities to optimize? Can we do better? Can we help create a better balance in these buildings? So that way we're not super oversized on heating, but just right-sized on cooling. We're also very limited in terms of the capacity of units that are available. So we may be actually potentially losing out on efficiency when we're super oversized in heating because the unit can't turn down as low as it maybe needs to meet these super low loads of heating. So I think there's actually an opportunity potentially to optimize, bring a better balance between cooling and heating loads. And as I mentioned before, I think PHI LEB can be a tool to help alleviate some of these design decisions that potentially are exacerbating the cooling load, which is the window SHGC in particular. And then the other elements of this is really, the higher the R value in the wall, the more thermos, the more of this thermos effect that we can create in the building. And that has an implication, particularly in the swing seasons when we want the building to actually help flush heat out, especially when we have an internally dominated building, a lot of internal heat gains. And in the summer or swing seasons, when it might be mild out, if we have a lot of insulation in the walls, we're trapping that heat in the building. And I think there's something to be said about, as I mentioned before in the example, PHI Classic, we had an R33 wall, and for PHI LEB, we had an R28 wall. Does that difference help us flush a bit more of that heat out in those swing seasons and help mitigate, again, the overall cooling demand in this case in these buildings? So um, I talked about a lot here. I want to leave enough time for questions. The last thing I will just say is that like I mentioned before, I've been doing passive house for a long time, worked on a ton of passive house classic buildings. I'm a firm believer in its effectiveness. We have data that I didn't even have time to show that shows how much lower these heating loads are, measured data compared to conventional buildings. I mean, we truly have done incredible work at smashing these heating loads down. But I view PHI LEB as another tool in my toolbox of options to help further improve these buildings and further improve the overall performance and design of these buildings. And it's not always going to be the answer for every building type. Um, I just think that particularly for multifamily, especially in these colder climates where we have um, very stringent climate files and things that make that heating demand very hard to meet. Um, but we have big buildings where we have a lot of internal loads and a lot of heat generated in the building. We need to think about cooling. It's only going to get hotter with climate change. And, this is something that I can confidently say keeps me up at night. So I am happy to get into questions. I don't have all the answers, but hopefully I can at least be helpful in enlightening folks about just sort of this topic. So thank you all for listening and let's
Yeah,
chat.
thank you, Dylan. Great presentation and a lot of good questions. We've answered some in the chat. We are going to run out of time here. I will say to everybody, put any questions you have in the chat. We can download it and I'll circle back with Dylan and we can distribute answers. There are a couple of things I do want to address, I think, that are kind of big questions. One is
Yep.
this conversation really has come out of Massachusetts in a way, where we've seen the demand for passive house and these projects coming online and your investigations of the different standards. And so it's our understanding, you know, well, two things. One, to just address the fact that we do see Massachusetts accepting low energy building as an acceptable certification to um, meet the code. However, I wanted to hear just a little bit more, Dylan, about and it ties into these projects, obviously, but where you make a push for low energy building. There's another question vis-a-vis cost, right? I mean, one could say it seems like low energy building would cost less, but maybe that's
Yes.
not necessarily the case. And so, how are you thinking about it as a consultant when you're talking to developers?
Yeah. Um, I don't think I said it explicitly, but I do believe that PHI LEB can result in a lower cost, first cost building, particularly because of slightly lower R value in the wall needed. The one thing I didn't talk about too much, but I mentioned in the one Middleborough example, R33 was required for PHI Classic, R28 was required for PHI LEB. Right around that area, R30 is where for a typical wall construction, let's just say it's a 6-inch steel stud cavity with insulation excuse me, in the cavity and exterior insulation on the outside, let's just say 4 or 5 inches. Right around that area of R30 or so is where you really struggle to, when you factor in thermal bridging and even with thermally broken facade attachments and all that, um, you really start to run into a limit in terms of how much R value you can get out of the wall without needing to add an additional layer of insulation, like a continuous insulation plane inboard of that stud cavity. So I do think wall R value is where we can see some help with cost. Window performance, um, the slight alleviation in the U value of 0.14 to 0.16 can potentially result in a slightly lower cost window, though you're still going to triple pane, so it might not have a huge impact. But I think, particularly on the cost topic, we're talking about these multi-building developments, right? Talk like thinking like that Heidelberg Village example or the two projects in Massachusetts I mentioned, where we're able to get the same window across all of those buildings. I think that's where we see a huge potential gain in or reduction in costs is when we can capitalize on the economy of scale and large bulk uh, purchases of products, essentially.
Right. Um, that really helps. One other quick thing I want to pivot and go to the quality side. You, I think, did a great um, explanations, great job of explaining, all these elements of passive house quality and why it's sitting firmly in that family. One thing that I just wanted to know and get your feedback is to the numbers. So when you showed the differences as a percentage and the heating demand doubles, I think that's one thing that everybody kind of like goes, oh, what's going on there? But then you realize that, and is this the case that these buildings, what we're seeing often is a 90% reduction in heating demand from what we might see out there, or some
Mhm.
some comparable dramatic drop. Uh, so if you're doubling it, in that case, you still have an 80% demand drop. So you're still gaining those climate objectives and energy efficiency objectives.
Yeah, absolutely. I think this comes back down to the idea of optimization and balance in these buildings. And um, the heating demands are already so much lower than conventional construction that a double of the already really low number is still a substantially lower value than what conventional construction is. So that's one element of it. I also think that for multifamily buildings, we still have work to do in more accurately predicting internal loads in these buildings. And if you were to look at the actual internal loads of operational multifamily passive house buildings, I don't know this for a fact, but this is my conjecture, is that it's higher than what the assumption as a standard is in the PHBP energy model. And if you were to factor those more realistic internal loads into the project, you'd see that what you thought maybe was doubling at the LEB standard is probably much similar to what you were modeling under the PHI Classic scenario, just with those more realistic internal loads. So I think
Right,
it's like an
because you've got a
opportunity to almost recalibrate those loads. Yeah.
more conservative calculation and you're
Yeah. So
uh,
it's yeah, a couple factors there, but
yeah,
I
yeah,
think
yeah.
internal loads
And
plays a big role.
what I mean, there's a number of things going on here, and would love to have you back sometime and dive into more of this. I think one thing just in our parting here, we do have to jump off. I
Yep.
apologize, our timing snafu. Um, but it comes up and again, the importance of windows and figuring those out and nailing them down
Mhm.
as absolutely mission critical. So thank you, everybody. We'll come back through the questions and follow up as needed. And really appreciate everybody joining us. And thank you, Dylan, for this effort. And look forward to returning to the subject in the future. I think there's a lot of interest, and it's, as you say, a very important tool in the toolbox.
Absolutely.
Thank
Thank you
you.
very much.
Have a great day, everybody.